Started here. Okay, we're on. Welcome back. Hope y'all had a good spring break. Welcome back to part 2 of Precalculus. So we're going to be kind of busy here for the next 8 weeks, right? Because, well, it's just the nature of things, right? It's going to get busier as we get further into the semester, trying to finish stuff. And keep in mind, this is a 5-hour class, right? So this class is going to demand more of your attention than just a regular 3-hour class. It's just built into the course. It's not just the length of time that we're in class each day. It's also the amount of work outside of class. So so that may feel like it's getting magnified here at the end of the semester, but that's just kind of the nature of the class. We've got some homeworks. So you're familiar with those, except there's a new one that's posted there on composition and inverses, which we're going to start talking about today. And so that's going to be a little bit familiar to you, but as usual, we may cover it in a little bit more depth than you're accustomed to from past courses. We've already talked about average rate of change and transformations, but I want to look a little bit more at transformations because we did that got a little bit muddled last time. So I want to go, and since we missed a week because of spring break, I want to go back through some of those homework problems from transformations. But there's also a problem on average rate of change. So I moved that back to today. So that's due tonight. There's not too many problems on there, and a lot of them are graphical problems. So although they do involve some computations, they're a little bit easier because the computations are derived from graphs. But there is one problem that does require a little bit more algebraic skill, and we didn't do an example like that in class. So I want to look at that one for you, because that one's likely to stump you. I don't know how maybe the online help is good on that problem, but I'm not sure. So it's this problem, the close to the end here, where it's a very simple formula, but computing the average rate of change turns out to be a bit complicated just because of the nature of the formula. So anyway, there it is. You've got a function. They're using an input variable of a t, but don't let that bother you. That could be x. And they want to find the average rate of change of the function between a and a plus h. Okay, so that's pretty typical. And so it's kind of easy to start the problem, but then, as I mentioned, maybe the algebra gets a little bit confusing. So let me lower the screen and then show you how to work on this one. Let me see if I can find some place here to write in my notes. All right, so I got a blank sheet here, so let's try this. So let's see, that formula was f of t is 2 over t, correct? So a really simple formula, right? But when you start, so it seems like the average rate of change would be easy to calculate, but when you start executing the steps here, that's when it gets a little bit confusing. And we want to find the average rate of change from t equals a to t equals a plus h. Well, that's not unusual for computing average rate of change. So just remember, your average rate of change formula, right, is just the same as the slope formula, right? So you're going to carry out this calculation, f of a plus h, right, minus f of a, and then divided by a plus h minus a, okay? So that is really just the slope formula, right? Okay. This is the y value associated with when x is a plus h, or when t is a plus h, and this is the y value f of a when t is equal to a, right? So this is y2 minus y1 over x2 minus x1, just the same as the slope formula, it just looks different, all right? Okay, now, once you've got that step, okay, in most problems, That's really the key step. It's just remembering, in most of these average rate of change formulas, the key step is remembering how to compute average rate of change. But in this problem, it's not, it turns out to be not quite that straightforward from here to simplify the algebra. So f of a plus h is going to be 2 over a plus h, right? You're just substituting a plus h for t here in your function formula. And then f of a, also equally easy, right? That's going to be 2 over a. All right, so you get what's called a complex fraction because you have a fraction and embedded inside of that fraction are some smaller fractions. Of course, the denominator of the big fraction is really easy, right? A plus h minus a is just going to be h. That's usually how the bottom simplifies, right? In these average rate of change computations, you just end up with dividing by h. And then the hard part is, right, is simplifying the numerator. And then at the end, you divide by h if you can't, right? So let's see if we can simplify this complex fraction. Again, complex fraction is where we have a smaller fraction, smaller fractions in this case embedded in a larger fraction. There are various ways of simplifying complex fractions. And this is a subject that's usually taught in the beginning algebra class, but of course, most people forget it, right? Because it seems like it's such a specialized topic. And it only comes up infrequently, but when it does come up, it's important. One way you can simplify this complex fraction is add these two smaller fractions in the numerator together, okay? So combine the 2 over a plus h minus the 2 over h. So in other words, do this subtraction of fractions. And to subtract these two fractions, you're going to have a common denominator, right? Because these two denominators are not the same. A plus h is not quite the same as a, right? So you need a common denominator, and so you have to kind of, reach back into your memory, right? And remember, how do I get a common denominator for these two fractions? But the simple way here for finding the common denominator is just take the product of the two denominators. That always gives you a common denominator. By the way, when you're adding or subtracting fractions, just take the product of the two denominators. The denominator is not the same, and you need a common denominator. That's not often, though, I shouldn't say often, but that's not always the least common denominator, though. That's not always the smallest common denominator finds, but it will work as a common denominator. So in this case, what I want to do then is add these two fractions, and so that, let me leave myself some space here, so that I end up with a denominator of, that's the product of these two denominators, a times a plus h, right? The reason I left myself a little bit of space here is because I'm going to have to transform these two fractions, right, so that they have this common denominator of a times a plus h. So look at this first fraction. What's missing from its denominator, from this common denominator? What's missing? See, you want this to have a denominator of a times a plus h, and now you have a denominator of just a plus h. So what are you missing there? A, right? You don't have that factor of a. So you're just going to create that. You're just going to multiply the a into the bottom so that the denominator will be a times a plus h. But of course, you don't want to change the fraction, right? So to compensate for multiplying into the bottom, you have to also multiply into the top. Okay. So in other words, to make a long story short there, I'm going to multiply top and bottom by of that first fraction by a over a. See, and a over a is just 1. So you're not really changing this fraction, but you're going to make it look different. Same thing here, right? For the second fraction. So what's missing from the second fraction there?
A plus h.
Yeah, a plus h. So I'm going to multiply that into the top and bottom, just like here. So into the top and bottom, I'm going to multiply in a plus h. All right, so let's see what we end up with. Well, we're going to have a common denominator, right? Because both of these denominators will be a times a plus h, exactly like I want it, right? And let's see what we're going to have. So we can add these two fractions, or in this case, we can subtract these two fractions. And let's see what we get now when we subtract these two fractions. Well, this first fraction is going to be 2 times a in the top, right? So you'll have 2 times a in the top here, subtracting off what? what's this second numerator going to be? 2 times a plus h, right? So you get something that looks like this. So you see the algebra is a little bit complicated already, right? Again, how did I come up with this fraction? Well, my common denominator is going to be a times a plus h. Both of these fractions have a denominator of a times a plus h, so I can subtract them. What's the first top here? What's the first numerator here? It's 2 times a, right? And then we can subtract off the numerator here, which is going to be 2 times a plus h. All right, now let's see what that, now let's start simplifying, okay? So this bottom stays the same. This is just h. Don't multiply the a times the a plus h, just leave it in factored form. So don't change this, but we are going to work on the top a little bit. So let's see, that's going to be 2a, this 2a minus, and then 2 times a, right? Minus 2 times a is minus 2a, and then minus 2 times h, right? And see, that's working out nicely already because what happens? Yeah, so that's, see, that's a very fortunate thing there, right? The 2 a's got canceled, correct? So I end up with still a complex fraction. So I haven't got rid of the complex fraction yet, but things are looking better. I have minus 2h over a times a plus h over all of that over h. See, that's still a complex fraction because I have a smaller fraction embedded in a larger fraction. Now I have to deal with the complex fraction. So the question is, how can I get rid of the complex fraction? So how do I not end up with a smaller fraction embedded in a larger fraction? The thing to do is to think about this fraction properly. Remember, fraction means division, right? So what you're really doing is you're taking this top fraction and you're dividing it by h, okay, right? But so it's to sort of write that out, what I just said, you have this top fraction minus 2h over a times a plus h, but I'm dividing it by h. So I'm going to write that as a division problem instead of as a fraction. Same thing, okay? You know, fraction just indicates division, right? But the reason I want to write it more formally as a division problem is one other thing I want to remember. Remember, dividing is the same as what? Taking the reciprocal and multiplying. So I can change this, this division into a multiplication problem by taking the reciprocal of h. And what's the reciprocal of h, of course?
1 over h.
1 over h. So what you really have here is minus 2h over a times a plus h times 1 over h. That's the same as dividing by h. Now, why is that? Why have I helped myself? Because what's going to happen here when you multiply?
The h's cancel out.
The h's cancel. Perfect. Yeah. Okay. So the h's end up just canceling. And that's exactly what I want. So I end up with minus 2 over a times a plus h, and just leave it like that. That's it. Okay. That's fully simplified. If you want to, you can multiply the a times the a plus h, and it's not going to make much difference. But you can just leave it in this form. Okay. So that's the result we're looking for. Okay. So what does that result mean? Well, at the time, for the time being, it doesn't mean much, okay, to us, okay. But in calculus, that result's really going to be useful to us, okay. We're really going to like seeing that. Really going to like seeing that result, okay. So we've achieved what we set out to do, okay. Yeah, it's kind of hard to know at this point in pre-calculus, you know, exactly what answer am I looking for here, right? You know, why is this answer useful to me? Well, it's kind of a mystery here, but that is indeed the answer that we want. Okay, while we have it here, if I can find it again, while we have it here, is there anything else from this average rate of change since it's due tonight? Okay. Anything else from this average rate of change that y'all have has caused y'all issues there? So this is a similar problem, except the algebra is going to be easier in number 7. All right, so not going to get that's hung up. Okay. In some of these graphical problems where you're computing average rates of change, you know, you have to read the graphs, right? So try to read them carefully so that you give you know, accurate answers to WebAssign, so that WebAssign won't count off. All right. And sometimes it's not easy to read those graphs too precisely, but try to do your best, okay, on those. Right. So other thoughts on that? Okay. All right. Let's switch over now to the here to the transformations homework, because I also want to look at some problems from that as well, since we just discussed that last time. As I mentioned, it got a little bit muddled. I think the homework problems are really easier than sort of the way I discussed it in class last time. Let me look and see what problems I had in mind here. All right, so 3, 5, and 12, and 13. Remember that for me. Okay, so let's look at that. Let's look at that problem number 3. This is not a graph, so and in fact, so this is a very abstract problem because they're giving you a function called f, so you don't even know what the function is, right? It's just some, you know, abstract function f, and you know they're talking about the graph of f, but of course you cannot graph f, right? Because you don't know what you know, you have no idea what the formula for f is, right? Okay, so so you just have to sort of imagine things. So you have this original function f of x, right? And here we have a transformed version of the function f. So we have applied here some transformations to this function f, right? Okay, and so we have some, you know, we have probably some shifts there, maybe horizontal or vertical shifts, right? And we may have some horizontal and vertical stretches, correct? Okay, and then they're just asking us basically to describe what those transformations are, right? So if you had a graph of f, correct? If you knew what the graph of f looked like, and you were asked to graph this new formula, 2 times f of x plus 9 minus 7, how could you graph that easily from the pre-existing graph of f, right, without having to go back through the whole process of applying, right? Okay. So how does the graph of this new formula compare to the graph of this sort of imaginary graph, right, of the original function f that don't even know what it looks like? Let's write down that formula. So 2, remember this for me. So 2 times f of x plus 9 minus 7. So your homework problem there is going to be slightly different for this particular problem, but similar. So the transformation homework is not due until I think I have it listed as Thursday. So you'll still have time to ask questions about this one on a Wednesday. All right, so let's see. What is that transformed function? 2 times, what was it? F of I'm sorry, I don't need that parenthesis. 2 times f of x, was it minus 9? And then here plus 7. Okay, what? Was it plus 9 also? Oh, plus 9 minus 7. So I got it backwards there. Well, of course, that makes a big difference, right? Okay, because changing these signs is going to, you know, completely change, right? The transformation. All right, now, as I discussed this last time, I was trying to convey the idea that that transformations you apply to the variable x, okay, they work the same when you apply those transformations to the variable y, right? And I just was trying to indicate that transformations of the variable y and transformations of the variable x. So when you transform the variable x, right, you're making transformations along x-axis, right? When you transform the variable y, you're making transformations vertically along the y-axis, right? But that got a little bit. I think that discussion got a little bit confusing. Okay. So let's start with this transformation where we're adding 9 to x, right? What does that? What effect does that transformation have, right? So when you add or subtract a constant from x, how does that affect the graph of the? How does that affect the graph of the function? It makes a shift right or left, right? So it just takes the entire graph, right, and then just shifts it horizontally right or left, right? So it doesn't distort the graph, okay, but it just shifts it to the right or the left. And when you add a constant to x, right, okay, then, well, which is it? Shifting it to the right or shifting it to the left? Yeah, that's shifting it to the left, right? So I was pointing out last time, right, that it's sort of counterintuitive, right? Well, if I add 9 to x, I should be shifting in the positive direction, right? So I should be shifting to the right 9 units, but instead it's opposite. Okay, so we're shifting to the left 9 units, right? So let's write that down. So we know somewhere here in this process, right, we're shifting the graph right left, right 9 units. All right, now let's talk about these. Now let's talk about these other two transformations. Okay, these transformations are really not. So this is multiplied by 2, right? Okay, and then also here subtracting 7. These transformations are really not transformations of the variable x. Okay, these are really transformations of the variable y, because these two constants you can move to the left-hand side. Okay, you cannot move the +9 to the left-hand side because that's trapped inside the parenthesis, right? Okay, that goes with the function notation. So you cannot shift the 9 to the left-hand side, but the 7 and the 2 you can shift left-hand side. Now, let's think about what would happen then if we shift the 7 to the left-hand side. You would get what formula? You would see what? Y what? +7, right? Equals 2 times, adding extra parentheses that I don't need. 2 times f of x plus 9, right? Okay, and so you can see that's really a transformation of the variable y, which means that we're going to affect the graph vertically, right, along the y-axis. Now, the effect that we have is just the effect that we have along the y-axis vertically is similar, is symmetrical to the effect here we had for when we transformed the variable x, right? Here we're adding a constant to y. We're adding a constant to y. So that means we're going to be shifting the graph up or down, okay? And which direction? Down, right, okay? Because we're adding the constant to y, okay? So again, normally you would think of that as shifting up, right? Since you're adding a constant to y, but it's counterintuitive, just like it is for x. So we're really shifting the graph down. So let's write that. We shift down, and it's obvious 7 units, right? Now, look, you really don't have to. You really don't have to think in this in the way that I just laid this out. Okay, it's much easier to think about this transformation just leaving the 7 on the right-hand side. Okay, you can see, right, that if we leave the 7 on the right-hand side, what are we doing to the graph of f? We're subtracting what from it? 7, right? Okay, and so in other words, we're going to be moving the graph of f down 7 units, okay, because we're just subtracting 7 from it. So you really don't have to think of shifting the 7 to the. You really don't have to think of shifting 7 to the right-hand side Okay, I'm to the left-hand side along Y. I was just trying to point out that transformations that we apply to X are the same as transformations we apply to Y. They have the same, a similar effect on the graph, except the effect is vertical instead of horizontal. I think it's much easier just to look at this and say, oh yeah, I'm subtracting 7 units from F. That means I'm going to be shifting graph down, okay, right, by 7 units. Likewise with the 2, okay, likewise with the 2, you can see here, we're multiplying F by 2, right? So that means we're going to be amplifying, right? Okay, the size of the graph, right? Okay, since you're multiplying F by 2, right? Okay, that means you're going to be stretching the graph, right? You're going to be stretching the graph by a factor of how much? 2, right? In other words, you're going to be doubling there the size of the, you're going to be doubling the size of the graph. Okay, so the way to describe here multiplying the 2 is just I'm stretching by a factor of 2. In other words, I'm sort of doubling there vertically the size of this graph. But last time, the way I described this was again maybe a little bit confusing. Let's forget about the 7 for a moment. Okay, if you want to shift the 2 to the the 2 to the left hand side, how can you shift the 2 to the left hand side? Divide by 2, right? Divide both sides by 2, so you get y over 2 is equal to f of x plus 9, and then of course y over 2 is the same as 1/2 times y. So you can see there that since you're multiplying y by 2, you're stretching the graph right now. Though, okay, you're stretching the graph by a factor of 1 over 1/2, all right? But how much is 1 divided by 1/2? That's 2, okay? So we're stretching the graph by a factor of 1 over 1/2, but that's the same as 2, okay? All right, let's look now at, so altogether, let's see what happened here. What was the right answer to that particular question? Let's see, we shifted it, oops, let's look back and see what we did there. What did we do? We shifted left, right, down, and then stretched by a factor of 2. So we shifted left, is that on here? That's here, right? Okay, and we stretched vertically by a factor of 2, correct, right? And then did we go down 7 units? Oh, that was it, right? So it's this one, correct? This one's not correct because we didn't stretch horizontally, right? And this one's not correct because we didn't shift up. So the right answer there has to be B, correct? Okay. All right, so now this one is pretty easy to answer too, just by looking at the previous example. We're doing what here? We're still stretching vertically by a factor of 2, right? Except how are we shifting? Yeah, right 9 units and up 7 units, right? Okay, so right 9 units and up 7 units. Is this the correct one? Is it this one again, the second one? Yeah. Oh, so I have to stretch vertically. Is it this one? This one? D? Right, stretch vertically by a factor of 2, then shift up. That's correct, right? Is that what we did? Shift up, right? Because we added 7 to F, right? So we shifted up. And then right 9 units, yeah. And then stretch vertically by a factor of 2. Well, let's try another one. See if we've got it. All right, so the next one I wanted to look at, I think, was, what did I say, 5? All right, so let's see if we can do 5. Oh, that one's almost too easy, right? And so here, we're just asked to fill in the formula, correct, right? So we just want to take the whole graph and shift it up 3 units. So how do you shift that whole thing up 3 units? Not right or left, right? So you're not subtracting from x, correct? Yeah, you're really subtracting from y, correct? Let's write down the formula. So we have f of x is equal to x squared, but think of this as y is equal to x squared instead of f of x is x squared. So in shifting up, we subtract what? 3 units from y, correct, right? So we would have this, but now you can just move the 3 to the other side and you get what? Plus 3, right? In other words, to shift up 3 units, just take 3 and add it to the, okay? Take 3 and add it to the, that will shift the whole thing up 3 units. Now, how is that different from adding or subtracting 3 from x? If you add or subtract from x, let's try adding 3 to x. This is the formula you write down, okay? So you add 3 to the x. So you would have x plus 3 squared. What does that do? Yeah, shift it right or left. Which way, Emil? Since it's x plus 3, you're going which way? Left, right. So that shifts the whole thing left 3 units. This shifts it up 3 units, right? So, so you can think of this as well. I'm subtracting 3 from y, but it's faster just to think, oh yeah, I'm taking the whole formula for f, which was x squared, and I'm just going to add 3 immediately to that, okay? The next one I was thinking, I think, is 12. All right, so here we've got some graphs. So where's the original function? I think it's this, the red one, right? Okay, so that's some sort of parabola. That's what that curve is called, a parabola. And so that has a simple formula, but not as simple as a straight line, right? Okay, but still a pretty simple formula. And so the first thing we're asking for here is, what would this graph look like? So 1/3 of f. See, there you're taking the entire function, not just the x, right, but the entire formula, and you're multiplying it by 1/3. So what that does is it does stretch it vertically, okay? It stretches it vertically, right, by a factor of 1/3. It's just that simple. So if you stretch it by a factor of 1/3, what's that doing? It's not really stretching it. It's what? Shrinking it, right, by a factor of 1/3. So Emil, which one? 2? I think so also, right? Okay, that looks like that's just been squeezed a little bit, right? Okay, so I think you're right. Now you can move the 1/3 to the left hand side by multiplying both sides by 3. So you would have 3y equals f of x. Notice there you're multiplying the y by a constant. That means you're stretching or shrinking it. You're shrinking it by a factor of 1 over the constant. The constant would be 3, so 1 over 3 is 1/3. Exactly what we said, right? We're shrinking it by a factor of 1/3. I said there, maybe I better write it down. So what I said was, here we have y equals 1/3 f of x. You can move this constant to the left-hand side by multiplying both sides by 3. So you have 3y is equal to f of x. So we can see there, right? We're multiplying y by a constant. That means we're stretching or shrinking. And we're going to be shrinking in this case, by a factor of 1 over this constant, which is 3. So in other words, we're shrinking by a factor of 1/3, just what we said. What is this thing? Oh, better select that. So what was that? Graph 2? What does that do now? So the +4 is pretty easy, right? That's going to shift it what direction? Left, right, by 4 units, right? So it's been shifted left by 4 units, correct? So it's got to be one of these over here, right? Because we've shifted that thing left by 4 units. But what's the effect of the minus sign now in front of the F, not with the X, but outside of the function notation? It rotates it around the x-axis. That affects it vertically. Okay, all right. It rotates the graph. Okay, when you rotate a graph vertically, you're rotating it around the x-axis. Okay, so it is a vertical effect. All right, but the way you describe it is I'm rotating around the x-axis. Sounds like a horizontal effect, but it's not. So which one of these has been? Is it 3? Yeah, that's been rotated and shifted, right? Okay, I guess that's correct. So looks like 3. That one's pretty easy to describe. What does that do? Shift to the right and up, right. Shift to the right and up. If you brought the 4 to the left-hand side, you would have y minus 4 equal f of x minus 4. So it's the same thing happening to both the y variable and the x variable, right? You're shifting, in this case, right, and here up, okay? So is that this one? So that's got to be graph 1. And finally now, there we're putting the minus sign inside the parentheses instead of outside. So we cannot transfer that minus sign to the, left-hand side, okay? Because it's stuck inside the function notation parentheses. So what effect does that have? That also is a rotation, but around the y-axis. That's a horizontal rotation. So a horizontal rotation means around the y-axis. So that would look exactly like f, except rotated around the y-axis. That's this one, right? Okay, because we took that entire red graph and just rotated it around the y-axis. If you rotate, this point is going to stay in the same place, okay? And all these points are going to get shifted over there, and there'll be their mirror image around the y-axis. So that is what, 4? So we must have gotten them all. Looks like the same sort of problem. Except now we're making multiples of not y, but x. So this 2, here's the original function f. This 2, you cannot get that to the left-hand side, okay? That is just multiplying x by 2. And what effect does that have? So that's a stretch, but in which direction? Yeah, that's a horizontal stretch by a factor of what? Not 2. 1/2, right? Okay. Yeah, okay. You always take the constant that you're multiplying y by or x by and divide that into 1. Take the reciprocal of it. Okay. So you're stretching by a factor of 1/2. When you stretch by a factor of 1/2, that's shrinking, correct? So you're shrinking this graph in the horizontal direction. Is that this one? I think. Oh, there's more. Oh no, it's this one. This one? Let's see. We originally had 1, 2, well, I don't know, 3, 4. I don't know how this is marked off. Up to what? 1, 2, 3, 4, 5, 6. Oh, the original is the red one. Oh, so that went 1, 2, 3, 4, 5, 6, right? But now it should get shrunk. This intercept should be back here, right? At 3. So there's only one graph that matches that, right? This one? Yeah. I don't think though. Okay. I don't think though that point. Well, maybe it does. Okay. So I was thinking that point should not get, that point's a little bit higher here than here, right? Wasn't sure that point would get elevated. Huh? It's the same, huh? Oh, on the red one. Oh, I see. Yeah, it's the same. I keep looking at this as the original graph. Okay. Yeah, it is the same. That point is 1, 2, and so it's not going to be 1, 2, but it should be at the same height, okay, which is 2. The graph is not being stretched vertically; it's only being stretched horizontally. So it shouldn't be taller; it should be just skinnier. Okay. So this one. And what effect then does the 1/2 have? It would be the opposite, right? You would be stretching by a factor of 1 over 1/2. 1 over 1/2 is 2. So we're stretching by a factor of 2. So we're lengthening this thing by 2. Which one is lengthened by 2 here? D, this one? so B is the only one I think that looks like it's even close, right? Okay. So yeah. So these intercepts are kind of the telltale thing, right? Originally you had an intercept at 3 and one at 6, correct? Now you have one at 6 and one at 12. Yeah. So so that looks like that's been stretched by a factor of 2. Shall we submit that one? I get it right? How do I know? Oh, yeah, I did. Okay. All right. Okay, does that help some? A little bit? Okay. Compared to what we left with last time? All right, let's try one more, a little bit different problem. So I have this as a recall practice, but we're not going to do it as recall practice. Because you can apply this same idea to to any type of curve, right? It doesn't have to be a function. So you can transform other types of curves that are not functions. So here I have an ellipse. That's the blue ellipse. Okay, I've got 2 ellipses there. All right, but the one I'm focusing on originally is blue ellipse. And I'm going to shift that blue ellipse, just shift it to the up and to the left. You can see, right? Okay, to form this red ellipse. So so this blue ellipse has its original center at 0, 0, like other ellipses that we've been looking at in the course. And I'm going to shift this ellipse so that its new center becomes -2 and 6. Okay, so clearly that's been shifted up and to the left. And what I want to know then is, what I'd like to write down is, what's the equation for this new red ellipse? So let's see if we can write down the formula for the new red ellipse based on our knowledge of transformations. But first we have to write down the formula for the original ellipse, right? Okay, so we're not going to be able to write down the formula for red ellipse until we write down the formula for the blue ellipse. So let's try writing down this formula. But I think we can remember enough about ellipses, right, to write down the formula. So this ellipse is elongated along the x-axis, right? So that means the denominator under x squared is going to be the larger, right? So that would be a squared over that would be x squared over a squared, because remember the a value is the larger, right? Plus y squared over b squared is the smaller of the a, b, and c, right? Remember that we use with ellipses, and this is always equal to what? 1, right? Okay, so the right hand side is easy to write down. That's always equal to 1. We just have to figure out what the a is and what the b is. But the a is easy, right? What's the a going to be here? Can y'all see it? Must be what? 4, right? It's going to be 4, right? Remember the a is always going to correspond to one of the intercepts, right? In this case, it will correspond to the x-intercept because this graph is elongated along the x-axis. So the a value would be 4. So you get x squared over 16, right? 4 squared plus, and then now what's the b value? 2, right? Because the y-intercept is 2. So y squared over 2 squared, which is 4, right, is equal to 1. So there's the equation for the blue ellipse. So simple to write down, right? Just x squared over 16 plus y squared over 4 is equal to 1. Now let's see if we can write down the equation for the red ellipse, which has been shifted up, correct? And by how much? 6, right? It's been shifted up by 6, right? Because your original center here was at the origin, right? And your new center on the y-axis is at 6, right? So that means this thing has been shifted up by 6. And how do we shift an equation up by 6? So what variable do we transform there? The y, and how do you transform it? Subtract something, right? Yeah, you want to subtract, correct? To shift up, you want to subtract from y. How much are we going to subtract from y here? Obviously, 6, right? So in this formula, just subtract 6 from y. So you would write down not y squared minus 6, but y minus 6 squared. You're going to subtract 6 from the y, okay? And so subtracting 6 from the y will happen before you square. And again, it's still over 4. That doesn't change. Plus, well, now what about the x? So we shifted horizontally how? To the left by 2 units, right? Okay. And so how do we incorporate that into our formula? Add 2 to x, right? So you would have x plus 2, x plus 2, and then square that. Okay? Instead of x, you would write x plus 2. And still over the 16, and then all this is equal to 1. So there it is, just that easy. Okay. So not that hard to write down the formula for that transform ellipse. Okay. All right. Let me save that. So, well, there's our review there of, there's our fast review there of what we discussed last time with transformations. Now, we're going to apply transformations to help us study, not really ellipses, okay, but to help us study graphs of trigonometric functions, okay? That's where we'll really be using ellipses. But that's not the only place, I'm sorry, transformations. That's not the only place transformations are used though, okay? But that's where we will really apply. All right, now before we get back to talking about graphs of trigonometric functions though, I have to introduce one more just a general idea about functions, okay? So we've been taking kind of a tour of sort of advanced function topics here after we finished our first go around with trigonometry, okay? But we're going to get back to trigonometry and a deeper study of the 6 trigonometric functions. But first we have to, again, as I mentioned, introduce some ideas from some advanced ideas just from functions in general, okay? So these things we're studying now, like transformations, and we also studied function direction, right? These ideas apply to any sort of function, but we're going to apply them specifically to, in a moment here, or in a little while here, to trig functions. All right, so but the other idea I need to introduce before we get back to the trig functions is how we combine functions to form new functions, or how we, I don't want to use the word transform because we've already used the word transform. So how we change functions to create new functions. What? Manipulate. Okay, yeah, there's a good, that's a good term too, right? So how we manipulate existing functions to create new functions from them, okay? And there are lots of ways of doing this, but we're going to study the three primary ways. Now, the easiest way to understand is just using arithmetic, okay? So you can take arithmetic, the four basic arithmetic operations, addition, subtraction, multiplication, division, right? That you've been familiar with since grade school. You can use those operations to take pre-existing functions again and create new functions from them. And so you probably learned about this before, okay? And let me just remind you what we call the arithmetic of functions. So suppose you have two functions. You got to start with two because you know, arithmetic usually requires two things to operate on, right? So suppose we have two functions. It really could be the same function, but you would have to duplicate the same function. So let's assume we have two different functions here, f and g. All right, and let me show you how we take arithmetic and create new functions from those. Okay, so the simplest way to take two pre-existing functions and combine them is just by adding them together. Okay, so in other words, you just sort of think of it as adding the two formulas together, combining the two formulas with addition to get a new function. Okay, when you add these two pre-existing formulas together, you get a new formula, right? Okay, and you can think of that new formula as being the formula for a new function. Now, if you wanted to, you could give that new function a new name. The name I gave to these pre-existing functions was f and g. But if you wanted to, you could create a new name for that new function. You call it h or s or, you know, whatever thing you can think of, right, as the name for that new function. But that gets a little bit tiresome after a while, having to create new names for functions. So we have a convention here, a naming mechanism that we use in algebra for indicating the name of this new function. And that the name for that new function, we're going to write down as f plus g. Okay, right? Makes sense, right? Since we're creating this function by adding the two pre-existing functions together. But I want to remind you that f plus g is the name of a new function. Okay, so that's sort of one unit, right? It means the name of, it's the name of this new function you've created. How did you create it? By adding the formulas, so to speak, or the two given functions together. So this is called addition of functions, obviously, right? Like addition of numbers. Now, you can pull this same trick with the other arithmetic operators as well. So you can also form a new function by subtracting two functions, right? Okay, and the name we give to that new function that we create is, by subtraction, is f minus g of x. Oh, by the way, that's the way you read this off the page, is f plus g of x. But again, that f plus g is the name for this new function you've created. You can also multiply functions together, right? Okay, and create a new function that way. Here's how you give a name for that new function. Just write f times g, okay, of x. What now? Oh, for what I have in the margin? Yeah, I'm gonna, I have to explain what's in the margin there, though. So I'll get to that in a second. All right. So this is just kind of an illustration. This is not anything you have to remember. Okay. And then you can also take the quotient of two functions, right? You can divide one function by another to create a new function. And there's the name we give to that new function. It's f over g of x. All right, we're gonna try this creating new functions using these operations here with an example in just a second. But the basic idea is we can combine two pre-existing functions using arithmetic to create new functions. Now, in practice, however, this is we usually don't go in this direction. We don't start with two existing functions okay, and then add them or subtract them or multiply them or divide them to create a new function, okay? We usually go the other direction. We'll be starting with some given function that may be kind of complicated, all right, for some reason. Its formula is complicated. And usually what we want to do is think of that or break that down as the sum or the product or the difference or the quotient of two simpler functions. Because when we take a complicated function and we break it down as the combination of two simpler functions, that often allows us to understand better the more complicated functions based on what we know about the simpler functions. All right. So, so the way we really use arithmetic of functions is sort of opposite of the way it's being presented in notes. Okay. All right. We don't usually take two functions and add them together, for instance. Instead, we take one function and see if we can break it up as the sum or some other arithmetic operation of two simpler functions. Okay. That's usually what happens in calculus. Okay. So this is a formula that shows up in calculus, okay, that you'll use repeatedly, all right, okay, in calculus. And the way this formula is used in calculus is exactly the way I described, okay? If we have some complicated function, it helps us understand it as maybe the sum of two simpler functions, because those two simpler functions may be easier to work with than the original complicated functions. Okay, well, let's practice this a little bit. It's so easy to do, though. Okay, so you've done this before, and this is not going to be difficult for you, except maybe sometimes the algebra might get a little bit tedious. Okay, so let's start with these two functions. Here's a function f of x equal 3x minus 4. So you know a lot about that function already. What sort of function is that? That's linear, right? Okay, so there's a linear function. So you can already imagine what its graph is going to look like, because you know its slope is what? 3, and its y-intercept is 4, right? So, or minus 4, correct, right? So there's an easy function to, there's a function you know all sorts of things about. The second function now, x squared minus 2x minus 3. So that's not a linear function because you have x squared in the formula. So that can't be a linear function. But that's not too bad of a function. This is not too hard to graph. When you graph this, you get a parabola, okay, the type of curve that I mentioned earlier. Okay. All right, so we're going to take these two functions and we're going to combine them to form some more complicated functions. Let's see if we can write down the formulas for these new functions. So first, let's write down the formula for this new function f plus g. So keep in mind, this is an entirely new function created from these two pre-existing functions. So this is the name of a function. Let's see if we can write down its formula now. So the name of the function is, again, f plus g. And how do we find f plus g's formula? Well, you just take the formula for f and you add on the formula for g, okay? Just like that. So let's see, what was the formula for f? We've got it written down up there, right? 3x minus 4, right? And we just add on the formula for g, which is x squared minus 2x minus 3. And there it is. Just that simple. We can add some like terms here. So we end up with x squared, and then you have 3x minus 2x is x, right? And then minus 4 minus 3 is minus 7. Did I do that right? I think so. Okay. So there's my formula for the function f plus g. So see, that's a completely different function. I don't know if it's completely different, but that's a different function, right, from the original two functions, f and g, that we started with. Let's try finding f minus g. That's just as easy, right? So f minus g, keep in mind, f minus g, that's the name of a function, right? But what's its formula? Well, you find that by taking f of x and subtracting off g of x. So we have 3x minus 4. That's the formula for f, right? Now we want to subtract off the formula for g. Make sure you subtract off the entire formula for g, or you're going to make a sign mistake here. So put the entire formula for g in parentheses. That formula for g was what? X squared minus 2x minus 3, right? So put all of that in parentheses, otherwise you'll get a sign mistake at the end. So I have 3x minus 4 minus x squared plus 2x plus 3. And let's see, what like terms can I add together there? There's only one x squared term, right? So that's minus x squared, and then what? Plus 5x? And then minus 1? Yeah. So there it is. Just the formula for f minus g of x. So notice the way you read that off the page. F minus g, that's the name of the function of x. Now, the one that's probably the worst is f times g of x. So again, the name for this function is fg or f times g, but its formula you find by multiplying the formulas for f and g. So here you have to do some multiplication. So that's going to be a little bit worse than addition and subtraction, right? So you take the 3x minus 4, there's the formula for f, and you multiply the formula for g, which was what? X squared minus 2x minus 3. And now I've run out of room. And I've got this big multiplication. So you have to be a little bit patient with the multiplication, right? Remember to multiply everything in the first parentheses, every term in the first parentheses, by every term in the second parentheses. So just be patient with that. So you take 3x times x squared. That's 3x cubed. Oops, notice we've already got a more complicated function here because this new function is going to have an x cubed term in it. Okay, so that's worse than either of these two functions, right? So we have 3x cubed, and then 3x times a minus 2x, that's minus 6x squared. And then 3x times minus 3, that's minus 9x. And then minus 4 times x squared, that's minus 4x squared. And then minus 4 times minus 2x is plus 8x. And then minus 4 times minus 3 is plus 12. So there's our formula. We just have to add like terms together. So I have 3x cubed, and how many x squareds do I have there? Minus 10? Minus 10 of them. And then how many x's? Just minus x. Minus 9x plus 8x is minus x, right? And then is it just one constant? Yeah, I think so. Just plus 12. So not too bad, right? Now, these are functions, so we can evaluate them at specific inputs, right? These are functions like any other function. So we can use numerical inputs and evaluate these functions at number inputs, right? So f plus g of 2, f plus g of 2, let's see, what would that be? Well, do I have the formula for f plus g? Oh, yeah, I do, right? Because I calculated that a moment ago. That is x squared minus x squared plus x minus 7, right? So f plus g of 2 would be 2 squared plus 2 minus 7. So what's that? Negative 1. 4 plus 6 minus 7 is minus 1. So there's one way of evaluating f plus g of 2, because you have the formula for f plus g. And so you can just plug 2 into that formula for f plus g, and you end up with a result there of minus 1. However, there is a little bit of a shortcut here. If you want to evaluate f plus g of 2, and you don't want to go through all the process of finding the formula for f plus g, you can do this directly from the formulas for f and g. Let me show you what I mean. F plus g of 2, that would be the same as f of 2 plus g of 2. So all you really need to do is plug the 2 into the function f, plug the 2 into the function g, and then add those two outputs together. And you don't have to first find this formula. So sometimes that shortcut's helpful. Sometimes it's necessary. So let's see, what would f of 2 be? So plug 2 into f, right? What happens when you plug 2 into f? Can y'all do that in your heads there without writing it down? What'd y'all say there? What? 2, right, yeah. So when you plug 2 into f, you get 3 times 2, which is 6 minus 4 is 2, right? Now, what happens when we plug 2 into g? So if you plug 2 directly into g, what would you get? Let's see if we can do that. 2 squared is 4, right? Minus 2 times 2 is 4 again, right? So you have 4 minus 4, so that goes to 0. So you just get left with what? Minus 3. So you have 2 there plus a minus 3, but that comes out to be, of course, what? Negative 1. Well, we had to get the same answer either way, right? Okay. So if you didn't want to bother with finding the full formula for f plus g when you were evaluating f plus g of 2, you could just plug the 2 into the f and g separately, add those together, and you're going to get the same result. Let's see. So what about f times g of 0? We have the formula for f times g, right? So we could plug 0 into this formula, or we could just immediately use the formulas for f and g to compute f times g of 0. So let's try that. So f times g of 0 would be, that would be equal to f of 0 times g of 0. Well, that should be easy to calculate. What's f of 0? You plug 0 into f, what do you get? Negative 4. And when you plug 0 into g, what do you get? Negative 3. Minus 4 times minus 3 is what? Positive 12. So f times g of 0 has to be positive 12. Is that what we would have gotten if we plug 0 into the formula for? Yes. Yeah, there's the formula for f times g, right? You plug 0 into that formula, all these terms disappear and you get 12, right? Okay, so obviously same result. Okay, now I've got a tougher question, but this one's for y'all. All right. So we have the function f over g. Remember, f over g means that's a function, right? That's just a name for a function. So functions have domains. So what I want to know is, what is the domain of this new function f over g? So you got to remember, well, what's the formula for f over g? How do you find that? That's just the formula for f of x, right? Divided by the formula for g of x. So, you remember what those formulas are? Am I going to be able to get those on the screen? Fortunately not, right? There are the formulas. So 3x minus 4. That's the formula for f. And the formula for g is x squared minus 2x minus 3. X squared minus 2x minus 3. So see, there's the formula for my function f over g. That's a little bit messier function, but all I want to know is what's its domain. So you don't have to try to simplify this, just what's the domain of this function? Remember how to find the domain of a function like that? What do you do? Remember, what numbers can you plug in for x? That's what we're asking, right? Okay. So for that function formula, yeah, well, Hannah, ideally it would be all real numbers, right? Okay. I mean, that's kind of our default assumption. But what's the problem here with possibly, what's the problem with all real numbers, Hannah? In this formula. See, in this formula involves division. So you have to be careful to not do what? In division, what can you not do? -1? No, -1 is okay. What can we not What do we have to avoid in division? 0 where? Dividing by 0, right. See, you've got division in this form. You cannot divide by 0. So you want to make sure your denominator is not 0. So how do you make sure the denominator is not 0? Yeah, set the denominator to 0 and solve that equation. And then those numbers you have to throw out of the domain. Can you all set that denominator to 0 and solve that? All right, try that for me. Okay, let's see. So x squared minus 2x minus 3, set that to 0. Don't worry about the top. Okay, but just the bottom. Set that to 0 and solve that equation. Let's start. Excellent. Yes. Yeah. Yeah, so well, you got to practice. Start. Okay. So you have to. Yeah, 10 to 0. Yeah, and then solve that. That's right. Right. Yeah, this is something you'll have to. This has to be solving an equation like that has to have the second nature. That's like the second most frequent type of equation to solve. The most frequent will be a linear equation, where you have a linear formula set to 0. Just divide. Don't worry about the. We're only worried about what happens. Yeah, so those are. Excellent. Sure, you're right. So when you go by here, you're not. That's going to be right. So. Yeah. Yeah, try out the steps right now. Remember to step on the right one. Yeah, seconds. You don't put 0 in. You take a B. Set. Okay. All right. All right. So I've been checking on the class. So we're kind of about 50-50 on how to proceed there. What about you guys online? So someone online there, can you describe for me what to do here in trying to find the domain of this function? So I do not want to divide by 0, right? That's the issue in this function formula. So that's what keeps the domain from being all real numbers. So someone online there, help me. What do I do? Yeah, got to move a little bit faster than that. Y'all are boring the class here. So So someone answer that for me. Kenneth, are you there? If you don't answer me, I'm going to count you as not being here. I think you factor so, but Kenneth, you have to say more than that because there are lots of things there that I can factor. So what do I do? What do I factor? There you go. So, but why I'm factoring, Kenneth, in order to, when you factor usually to solve an equation. So what's the equation that I'm trying to solve? What's the equation, guys, that Kenneth is trying to solve? Right, we took the denominator, right? X squared minus 2x minus 3, right? That we set equal to 0 because we do not want the denominator to turn out to be 0. So we're going to check and see what x values will make it 0. Those are the ones we do not want in the domain, right? Okay. So, so Kenneth says this is how it factors. I'm going to factor x plus 1. I'm going to factor x squared minus 2x minus 3 as x plus 1 times x minus 3. Beautiful. That is my strategy for solving equations like this, where you have the x squared. If you didn't have the x squared, you could solve this with arithmetic, but the x squared makes it more complicated to solve. So my first choice in solving an equation like this where I have x squared is to factor. Sometimes that doesn't work, okay, right? But in this case, it works beautifully because x squared minus 2x minus 3 does factor as x plus 1 times x minus 3. Now, Kenneth, what conclusions can I draw from that? So see, the logic here is just so perfect, right? So I have this, Kenneth. So what conclusions now can I draw? Someone help Kenneth there with his logic. What? So, but there's a step before that, Jaquela. So you're right. X equal minus 1 or x equals positive 3. You're correct. But there's one little intervening step that I want to. If this product is equal to 0, that means that one of these two factors is 0. If x plus 1 times x minus 3 is equal to 0, that means x plus 1 equals 0 or x minus 3 equals 0. That's the key logical step here, okay? Right? If you have a product that equals 0, one of the factors has to be 0. In arithmetic, right? And you know this from very early in your grade school arithmetic, right? You know that if you multiply two numbers together to get 0, the only way that happens is if one of the two numbers is 0. So you know x plus 1 is 0 or x minus 3 is 0. But now, Jaquela, then know what x is, right? X must be what? -1, or x must be what? Positive 3. Exactly right. Okay. So those are the two numbers you cannot have in your domain. All right. So the domain here is, if you want to write it in words, it's all real numbers except -1 and positive 3. So it's almost all real numbers, Hannah. Okay. Pretty close, except just those two exceptions. All right. Cannot be in the domain. Yeah. You cannot take the square root the way it's written. All right. So, but that is, there are other strategies for solving equations like this one that are built on taking square roots. Okay. But you cannot, because that's a natural impulse, right? I want to take square root, correct, to get rid of the square. Yeah, and so there are strategies built on that idea for solving equations like this, where you have x squared in them, but they take a little bit of extra effort to massage the equation into a form that where taking the square root will work. Okay, so our first choice is factor. Okay, right. But that doesn't always work because you cannot always factor. Okay, so then you are left with plan B, which indeed involves square root. That process, though, is summarized in a famous formula called what? Begins with a Q. The quadratic formula, right? So the quadratic formula is our second, would be our second method for solving equations like this, right? And the quadratic formula involves the square root, okay? And so that square root comes about from trying to take the square root of both sides, but it takes a little bit of effort before you can take the square root of both sides, right? So look, folks, this is something you absolutely cannot go into calculus and be stumbling around, because the first time your professor sees that, he's going to lose all respect for you, right? And no, I'm serious. He's going to say, this student is not prepared for this class, and then he's going to dismiss you for the rest of the semester. You're going to be, he's going to have a low opinion of you from that point on. All right, I'm telling you, all right, that's just the way psychologically that's what's going to work. All right, so you don't want to be in that, position, okay, of trying to prove yourself to the professor for the whole semester. All right, so you've got to remember some of these basic things, okay, like how to solve a quadratic equation. This is called the quadratic equation because of x squared in it. And so your two choices are factor. If factoring doesn't work, it works beautifully here, so that's great. If you cannot factor, then you have to switch to plan B, which is the quadratic formula. Got to remember the quadratic formula. Okay, got to remember the quadratic formula. All right, or at least be able to tell your professor, yeah, I know I have to use the quadratic formula, but I need to look up the quadratic formula. I can't remember the details of the quadratic formula. He may let you get away with that. Okay, right? Okay. So that's just really that's just really elementary to I'm not trying to make you feel bad, okay? I'm just warning you that solving quadratic equations really elementary to undergraduate mathematics, and so you just really have to bite the bullet here and remember how to do this, okay? Teach yourself how to do this and so that you'll memorize it. Now, we have another way of, actually lots of other ways of combining functions to create new functions. So one way is using arithmetic, okay? There's another method that is kind of special to functions. So this does not have an analog in arithmetic. This is not built from arithmetic operations. So this method is called composing the two functions, okay? And so when you compose two functions, notice we use a special symbol for that operation because this is not an arithmetic operation. So we use what looks like a degree symbol. It's a little circle there, but we don't write it as a superscript like we would with a degree. We write it there between the two functions. The way you read this, though, is F compose G. That is the name for a new function, right? That's a name for a new function that we create from these two pre-existing functions, F and G. Now, how does composition work? How does this operation work? Okay, since it's not an arithmetic operation. So it's not addition, subtraction, multiplication, and division. All right. Well, it works as follows. You're going to take the one function and use it as input to the second function. So you feed one function as input into the second function. So see, that's an operation you can only do with functions. That's not an operation that has any meaning in arithmetic, right? Now, one thing that's not satisfying about the composition operation is it's not commutative. What that means is if you do the composition in the opposite order, you usually get a different result. Okay, so see, that's not true for addition, right? If you add two numbers in either order, you get the same result. Also true for multiplication, right? If you multiply two numbers in different order, you get the same result. But in composition, not commutative. If you compose two functions in different order, you usually get a different result. Okay, so G composed with F is usually going to be different than F composed with G. This looks like the word fog, but it's not, because that's a little like degree symbol. So again, how does G compose with F? How do we create that function? We take the function F and we use it as input to the function G. Okay, and then we simplify this formula, and whatever we get is the formula for G compose F. All right, well, let's take a break here then, and we're going to come back and practice with composition. You've done composition before. It's intuitively, conceptually, it's a really easy idea. Okay, all right, so of course it's not going to be as easy as arithmetic because you're not as familiar with it as you are addition, subtraction, multiplication, and division, right? You haven't been doing this since grade school, right? Like you have arithmetic, all right? But still, it's conceptually easy, right? Again, it's just another way of taking two pre-existing functions and building a new function from that, okay? And again, the main thing we do with composition is we don't start with two functions and just compose them. Normally, what we do, what you're going to do in calculus is you're going to have a complicated function. It's difficult to study, and you're going to try to break it down as the composition of two simpler functions, and the simpler functions will be easier to work with than the original complicated function. All right, that's really the way we use composition in calculus. All right, so let's stop there though, and let's take a break until about 11:35, since I've been running on here for a big feed. So let's take a break, and then we'll come back and practice a little bit with composition. Okay. All right. Thanks, Kenneth. Okay, so we'll start with the easy problem here. So we want to find F compose G. That's the way you read that off the page. F compose G, all right, of using at first just a number here, input of -1. So we're going to end up with a numerical result here, right? Okay, because remember, F compose G is just a function, right? This is just, we have this funny naming mechanism, right, for that new function we're creating from F and from the old functions F and G. So now when you're doing composition, it's really useful, I think, to be constantly reminding yourself of the definition of composition. So F compose G of -1 means you're going to take F of G of -1. All right. So you're going to take the -1 and first plug it into G, and then that result you're going to plug into the function F. All right. So you're feeding that one function as input to the second function. And then just follow the order of operations here, right? The order of operations says I'll compute G of -1 first, and then I'll compute F of whatever I get from that. So let's see, what is G of -1? Well, that's going to be whatever we get when we plug -1 into the formula for G, right? So that's going to be -1 squared minus 2 times a -1 minus 3, right? See, I'm just taking -1 and putting it in to the formula for G. If you want to, you can do all this arithmetic separately and then plug this number in, or like me, just kind of do it all in one line. All right, well, let's see. What does that work out to be? Well, -1 squared is 1, right? Positive 1. -2 times -1 is +2. And then -3. So is that, that's 0? Oh, nice. Okay. So we just end up here with F of 0. Now we have to calculate F of 0. So what's F of 0? Well, there's our formula, right, for F. So we have 3 times 0 minus 4, which is -4. That's it. So F of G of -1, all of that turns out to be -4. So see, just like with any other function, with the function F compose G, when you have an input, get this, you get a matching output, right? Let's see, what about G compose F of 2? So this is a slightly different function now, G compose F. Let's see how that one works. So we have G compose F of 2. What does that mean? That means G of F of 2. So this intermediate step is really important to write down. Remind yourself, G compose F of 2 means G of F of 2. Now we just have to compute F of 2. So F of 2, here we use the formula for F, right? So you have 3 times 2 minus 4, which is going to be 2. And now 6 minus 4 is 2, right? And now you calculate G of 2 using the formula for G. So we have 2 squared minus 2 times 2 minus 3. So that looks like negative 3, right? 4 minus 3 is negative. So G compose F of 2 is minus 3. Let's try we're going to come back to these functions F and G in just a moment, but I want to skip down here. These are two different functions, F and G, and but here we don't have the formulas for F, and well, I'm not sure if these are F. We don't have the formulas for F, and we don't have the formulas for G. But let's see what they're asking. We just have the graphs, but we don't have the. But they're saying, okay, find the Y-intercept of F compose G and G compose F. What a strange question. So got two functions F and G. You don't know what their formulas are, but you have their graph. So that's almost as good as having the formula, right? Not quite as good, but almost as good as having the formula. And we want to know what's the Y-intercept of these two new functions, F compose G and G compose F. So we've got this function F compose G, and I want to know its Y-intercept. How do you find the Y-intercept for any function? You set the input to 0, right? Okay, you set x equals 0. So to find the Y-intercept of F compose G, you're going to use an input of 0, because that's true for any function at all. And F compose G is just a function. Now, you may be wondering, but how do I find F compose G? Because I don't have the formula for F compose G, and I don't even have the graph for F compose G. But just remind yourself, what does F compose G mean? That means what? F of G of 0. So when you're doing composition, like I said here now 5 times in a row, right? Always remind yourself of what composition means. Okay, F compose G means F of G. Now, what's G of 0? Do I know what G of 0 is? Well, I don't have the formula for G, but I do have this graph, and it looks like on this graph, G of 0 is what? 3 right there, right? Okay, it looks like G of 0 is up here at 3, right? There's x equals 0, and it looks like the output at 0 is 3. So I think G of 0 is 3. But now what's F of 3? Again, I don't have the formula for F, but I've got the graph. So can we see it from the graph? Let's see, F of 3. There's x1, x2, x3. Looks like what? 1. There you go. So I have no idea what this function F compose G looks like when I graph it, but I do know one thing. Its Y-intercept is what? 1. Yeah, it's going to cross the, whatever this graph looks like, it's going to cross the Y-axis at 1. What about this function? G compose F. What is its Y-intercept? Remember, F compose G and G compose F are probably different because composition is not commutative, right? So you can't change the order of composition and get the same thing. So let's find the y-intercept of this function. So how do you find the whoops, got to do it in the right order. How do you find the y-intercept of a function? We just said what? Use input of what? 0, correct? So G compose F of 0. That means G of F of 0. Now, can I figure out what F of 0 is? What does the graph look like? There's 0. What's F of 0? -1. So it looks like what I really have to calculate here is G of -1. So what's G of -1? Let's see. There's -1. Looks like G is what? 2. Just that easy. See? Read those things from the graph. So it looks like for this function, its y-intercept is 2. Oh, so you can see these two functions not the same, right? F compose G and G compose F, they're not the same function because they have different y-intercepts, right? So whatever these two functions are, I have no idea. They're not the same, right? They don't have the same y-intercepts. All right, now let's go back to these two functions. So these are slightly different, f and g's. All right, so 3x minus 4 and x squared minus 2x minus 3. Let's go ahead and a moment ago we found f compose g of -1 and we found g compose f of 2. Let's find the complete formulas for these two functions. All right, so you know, we evaluated f compose g at one particular number, but let's find its entire formula. So in case we want to evaluate it for any number, not just -1, but for any number at all, we would have a formula for doing that. So let's find the formula. That means find f compose g of x. So you'll have a formula that works for any input x, right? And as I keep saying, right, f compose g of x means f of g of x. Work inside out here now, okay? So what's g of x? Well, I have a formula for g of x, right? It's x squared minus 2x minus 3. So don't forget the f is on the outside here. So you get x squared minus 2x minus 3 inside the parentheses. All of that is g of x. And now we have to calculate f of that. So how do you calculate f of x squared minus 2x minus 3? You have to take all of this and do what? Plug it into the formula for f, right? So you have to take all of this and go up here and plug all of that in for x, right? Oh, that's not too bad. So let's see, I get 3 times all of this, x squared minus 2x minus 3, and then you get that lonely minus 4 at the end, right? So that's it. Well, that's not too hard to compute. Just multiply the 3 through the parentheses, right? So you get 3x squared minus 6x minus 9 minus 4. And you can add the two constants together. So you get 3x squared minus 6x minus 13. So there's the formula for f compose g. So now if you want to evaluate f compose g for any number, you can just use this formula, right? Okay, you can go directly to the formula, plug the number in for x, and you're done. Let's see, does that match up with what we got up here for f compose g of -1? If I plug -1 into this formula, let's see, what do I get? I may have to write this one down. If I plug -1 into this formula, what do I get? I hope it turns out to be -4. Is that what it turns out to be? Let's see, you get what? +3, because -1 squared is +1 times 3 is 3. -6 times -1 is +6. And then -13. Yeah, that's 9 minus 13, which is -4. Okay. Well, of course, that had to be right if we algebra, right? But That gives us some reassurance that we did the algebra right. Okay, I'm going to let y'all guys do the hard one, because the hard one here is G compose F. So give you a little bit of workout with your algebra skills. So G compose F of X. I want the formula for G compose F. A moment ago, we found that G compose F of 2 is -3. But now I want to know what's the formula for, in general, for any X, not just 2. So remember, G compose F of X means G of F of X. So what's G of F of X? That's going to be a little bit messy, just a little bit. So try that on your paper there, right? See if you can find G of F of X. Remember, there's F of X, 3X minus 4. There's G. So see if you can evaluate this expression, evaluate and simplify this expression. I'm not sure what the answer is, so y'all are going to have to, someone's going to have to get it right. So we'll look at the answer. Excellent. Yes, I'll put the right spot here. It's kind of simple. Wow. So now, you know, yeah. Yes, that point. So, right. That made it nice. Huh? So, yes. Yeah. That will help. Second. So But not quite exactly the same. That's right. It's 3 times. Yeah. Perfect. Yeah. All right. That's good. That was good. Okay, let's see what we got there. Most of y'all got it really nicely. So g of f of x there would be g of, and then f of x is 3x minus 4, right? So wherever you see the f of x, just put in 3x minus 4. And now here's where the hard part starts, right? Because we have to take all of this and plug it into the function g for x, right? So so you'll have this formula, but you'll substitute 3x minus 4 for x. So you would have 3x minus 4 squared. What was that? Minus 2 times 3x minus 4, right? And then the minus 3 still there at the end. So that really is it. That's g composed f of x really is this formula. The rest of this is just algebraic simplification. Okay. So let's see if we can simplify this though. So 3x minus 4 squared is means you when you square something, you multiply it by itself, right? So you're going to have 3x minus 4 times 3x minus 4 minus 2 times 3x minus 4. That's a little bit easier. That's going to be minus 6x plus 8, right? And then don't forget the minus 3. It's easy to forget that, but it's still there. And now let's see if we can square this binomial. So 3x times 3x is 9x squared. 3x times minus 4 is a minus 12x. Minus 4 times 3x is another minus 12x. And then minus 4 times minus 4 is plus 16. And now you're just adding like terms together. So we have 9x squared. How many x's do I have here? Minus 12 is minus 24. Minus another 6 is minus 30x. And then my constants are 16 plus 8 is 24. Minus 3 is 21. So looks like that. Did y'all get that? 9x squared minus 30x plus 21. Well, at least hopefully you were on the way to this. Okay. Right? Didn't quite get, if you didn't get quite through all of that. Let me see what else I have here before we come back to that. Whew, now we have to talk about inverses. So let's do this one last problem, and then the topic of inverses is a big topic. So that's really crucial to us. So let's do this last problem for you guys before we finish here. We've got just enough time. So this is kind of like a proof, all right, but of a kind of an easy fact. If you have two linear functions can be any two linear functions at all. If you compose them, you're going to get a third linear function. So when you compose two linear functions, you get another linear function, right? So we want to demonstrate that that fact is true. Compose two linear functions, the result is also going to be a linear function. But we don't want to, we want to prove this in general, not just for two specific linear functions, but in general for any two linear functions. So here's what here's how we can start. Let's write down two just generic linear functions. What do linear functions look like in general? So I gave them the names f and g. That's not important. I gave them the names f and g. But remember, these can be any two linear functions. So I can't specifically write down their slopes, and I can't specifically write down their y-intercepts, okay? Because these have to be any two linear functions. So for this linear function f, let's just suppose it has slope m sub 1. This can be any slope, and its y-intercept is b sub 1. So this could be any number for the y-intercept. And then for the function g, it also has to be a linear function. Let's suppose it has slope m sub 2, because I want to make sure it doesn't have to be the same as m sub 1, right? And let's suppose it has y-intercept b sub 2, but doesn't have to be the same as b sub 1. So this is some linear function, and this is some second linear function, may be different than the first one. Now let's compose them, because that's what the problem says, right? So let's compose them. Let's take f compose g of x, and what I want to see is, does the result turn out to be also a linear function? So that result is going to be different from these two, right? Okay, but let's see if it also is a linear function. All right, so here's always the key thing to remember for composition. F compose g of x means what? F of g of x, right? So that's just a phrase you have to memorize, all right? F compose g of x means f of g of x. But what is g of x? What did I say it was? It's just this formula, right? So just put this formula in for g of x. Don't be bothered by the fact that you don't know what this number is, you don't exactly know what this slope is, or you don't exactly know what this y-intercept is. These are just numbers, okay? So let's just plug that in, all right? So we want to compute f of m2 times x plus b sub 2. All right, that's where I want y'all to start. See if you can take this, right, and plug that into the function f. You take all of this and plug it in for what? Into f. So, but where do you plug it into f? For x. Yeah, take all of that and plug it in for x. Do the arithmetic and see what you get. Okay. So do the arithmetic there and see what you end up with. Okay. It's going to look kind of funny, but if we look at it just the right way, we'll get what we want. All of that, plug that in x, see what happens. Okay. Yeah, that's b sub 1, and it's not b comma. I'll find that too. Yeah, right. It's really getting really multiplication. Kind of fun. So that's it. So I have that next. Yeah. So that's just. Yeah. Okay. You don't have to write your time. Yeah. Don't forget to stand on. There you go. See what's that. See what. Oh, so you're that. Slope. And what's the there we go. Okay, multiply that through, so you have. M1 comes in. And you just have to leave it like that. There wants the numbers. So you can't combine. All right. Let's see what y'all wrote down. I think y'all wrote it down really nicely. All right. So f of g, which is g is this, right, is going to be, take all of this and plug it in for x up here. So almost everyone wrote this down nicely. So you have m1 times m2 times x plus b2, right? Because you're plugging all of this in for x up here. And then plus you have just that b1 thrown in at the end, right? That's part of the formula for f. See, so that looks all kind of confusing. Let's go ahead and multiply the m1 into these parentheses, right? So you multiply m1 times m2 x. So you get m1, m2x. That's all you can write down. You really can't do anything with that, right? Because you don't know what m1 times m2 is, right? And then m1 times b2. So you just write that down, m1 times b2. And then plus b1. Okay, that's it. That's simplified. But now we have to deduce from this, is that really the formula for a linear function? If you graph that thing, if you knew what m1 and m2 were and what b1 and b2 were, right? If you graph this, would you get the graph of a straight line? Okay, Evan says yes, because Evan, you're saying, why is that a straight line? That's right. That is just a number, right? So you m1 times m2 is just a number, right? So you have this number times x. So the slope of this composition function is m1 times m2, right? Okay. The product of the two original slopes gives you the slope of your composition function. And what's the y-intercept then of your composition function? It's what's left over here, right? Notice m1 and b2 and b1, these are just numbers, correct? These aren't variables. X is the variable. So these are just constants. So when you combine those, right, you just get a single number. That is the y-intercept. So the y-intercept of your composition function is m1 times b2 plus b1. That one single value is the y-intercept. So you see, this is just a straight line, right? It's a number times x plus the y-intercept, right? Okay. So when you graph the composition, you get a line with slope m1 times m2. Maybe that's a big number for the slope, right? And then this quantity is where it's going to cross the y-axis. So that's kind of nice, at least. When you compose two linear functions, you don't get something really super complicated. You just get another linear function. Okay. All right. The next topic coming up then is on Wednesday is inverses. So inverse is yet another way of taking a function and creating a new function from the original function. So we've learned arithmetic, right? That's a way of taking two functions and creating a new function. We've learned proposition, and now we're going to learn what's called taking the inverse of a function that creates a new function. The inverse is a little bit different, though. Inverse only applies to one function. So you take just a single function and you create what's called its inverse, which is a new function. You know, for composition, you need two functions, right? Or for arithmetic, you need two functions. But for inverse, it's just a single function, and you create what's called the inverse of the of that function. All right. Okay, so we'll work on that next time. Okay. So I'll see you all guys on Wednesday. So don't forget you have a homework on what is it, on average rate of change, right? That's due tonight. I think that one's not too bad. Okay. All right. So let me stop the recording.